Okay. So I'm going to be talking about vertical asymptotes. And this is for like the second half, of the week 6 stuff. We start getting into rational functions. And then you're going to kind of pick up rational functions again at the start of week 7. So I figured since we're meeting at the end of week 6, this is a good topic to do, something that's sort of at the end. So it's vertical asymptotes, which are actually pretty simple. They're remarkably simple for something that you think, oh my gosh, I've got these fractions, but no, they're actually really simple. So these are properties of rational functions. So you need to know what a rational function is. And so we had rational expressions and we've had rational equations where basically we had something with variables in the denominator. So a rational function is a function. So you've got each input has only one output, but it has a rational expression in it. So basically it's a function that has a fraction. Your variable is in the denominator. When we have functions, these are usually things we're looking at graphs for. So part of knowing rational functions is kind of knowing what the graphs look like. And it's always written as one fraction. So you don't really have a fraction plus another fraction. It's usually combined as a single fraction. And so you'll have a polynomial on top and then a polynomial in the denominator. And of course, the denominator is not allowed to be 0 because then you're divided by 0, which we can't do. So rational functions have what are called asymptotes. So it's honestly, I don't know if it's a silent P or if you're kind of saying the P. Nobody's really actually told me, I kind of ignore the P when I say the word. But they are like straight vertical lines, or you also have horizontal. So they're horizontal or vertical lines, but they're lines that when you're graphing the equation, it gets near the line, but it doesn't actually touch the line. And we don't normally graph the lines. It's something that if you were to graph a line, it would be, if you were to graph what it's approaching, it would be a line. Sometimes we will graph these with like dashed lines to indicate that there's an asymptote there, but sometimes we don't put them in at all. So they're sort of like invisible lines of a graph that your function gets near but doesn't touch. So these are sometimes called limits. And if you have to go on to pre-calc and you have to go on to calculus, you're going to see the term limits again in both of those classes. So we have 3 different types of asymptotes: vertical, horizontal, and slant. And so I'm focusing on the vertical ones in this lesson. And if somebody is asking you about the behavior of a function or end behavior, it's sort of asking about those asymptotes. So, it may not strictly ask what are the asymptotes, but you have to know that if it's talking about behavior of a function is basically what does it do on the graph. And so that's where we're looking. Where does it go near? Are there certain values it's approaching? That's part of what we're looking at with asymptotes. So rational functions have vertical asymptotes, and pretty much they're the only type of function that has vertical asymptotes, because a vertical asymptote is formed when your denominator is equal to 0. And so if you have a denominator with a variable, it's automatically a rational function. So even if you didn't have a polynomial, if you have something else on your numerator, if there's a denominator with a fraction, it's a rational function. So rational functions have vertical asymptotes. So this is very specific to those type of functions. So this is what I said about we've got this line that sometimes will indicate dashed lines where the asymptote exists. And so it's for a vertical asymptote, it's a vertical line. And so the equation is x equals a number because that's the equation of a vertical line. So we learned that back when we were learning about linear equations, is that a vertical lines are x equals whatever the number is. So we've got a vertical asymptote if our function approaches that line. So the actual function we're looking at is the blue line. That's the part that would actually be graphed. And then you wouldn't necessarily graph the pink part. You would just see that your blue part is approaching and it starts to get straight. That's basically the key. You know it's approaching a vertical asymptote when you zoom out and your part of the graph starts to look like it's becoming a straight line. Technically, it's never becoming a straight line, but it starts to look like it. And that straight line it starts to look like is our vertical asymptote. So we've got our graphed function, and it either will go up or goes down. We know that, the y values are going to increase or decrease. And so what we have with this notation that you see here is it says f of x arrow infinity or arrow negative infinity. That arrow just means approaches. So as our function is nearing infinity or negative infinity, basically as high as you can go or as low as you can go, our values are approaching, our x values are looking like they're reaching this line. So the vertical asymptote is just what is the line that your graphed function looks like it's becoming, if you want to think about it that way. So when we're looking for vertical asymptotes from an equation, and that's what I'm focusing here, is finding it based off of the equation, you first need to factor the numerator and the denominator and then simplify if it's possible to do so. So when we were simplifying rational expressions, one of the reasons we had to learn how to do that is because you need to find vertical asymptotes. So if there are things in common, you cancel those out. Then whatever you have remaining, the simplified part, you take the denominator and you set it equal to 0 and solve for x. And that will give you the equation for the vertical asymptote. And you could have more than one equation. If you have like a quadratic in your denominator, then you'll have 2 vertical asymptotes. So the key is your denominator is equal to 0 after you simplify, and then you solve, and that gives you your equation for the vertical asymptote. So we're going to be solving a lot of linear equations. We're going to be solving quadratic equations. And so that's why you had to learn how to solve those types of equations. And you'll be factoring a lot. That's why I say, like, we use factoring like every week. Once you learn how to factor, you're going to use it a lot because we have to factor first before we can find vertical asymptotes. Now, one thing that I see people get confused on is vertical asymptotes and domain. And I see this a lot on quizzes. So they're similar because the domain of a rational function is also based off of the denominator. But for the domain, it's before you simplify. To find the vertical asymptotes, it's after you simplify. So the process is the same. You're setting your denominator equal to 0, but one is before and one is after. And with the domain, your values are not allowed. So it's like a not equals to part, and you write your answer in interval notation. For vertical asymptotes, you just set it equal to, and then you get an equation. You have an x equals a number for your vertical asymptotes. So the process is nearly the same, but how you give your answer is different depending on whether you're being asked for the domain or the vertical asymptote. And also when you set the denominator to 0 is different. So just keep that in mind, because I see a lot of people get confused between the two. Like if they find the domain after they simplify, but you're supposed to find it before you simplify, things like that. So all we're going to be doing is finding our vertical asymptotes. So that's what we're doing here. We're starting simple and then we'll get more complicated. So I've got 2 functions here. The first is -2 over x. So when you are finding the vertical asymptote, you first simplify if you can, but 2 over x can't be simplified. So you just set the denominator equal to 0. Doesn't matter if there's a negative in front there. We just have to set our denominator equal to 0. So we get x equals 0. That's your vertical asymptote. Like we don't even need to solve. That's it. You're done. So some of these are really nice, really easy. That is our answer. You just literally take your equation, your denominator, and set it equal to 0. And if you get x equals that number, then that's your answer. So the next one over, we have g of x equals 2x plus 5 over x squared. So same thing. There's nothing to factor out here. So I just set my denominator equal to 0. So we have x squared equals 0. Now here, I don't have x. We want to solve this equation. And so we're going to take the square root of both sides because we have x squared. So if you have x squared equals a number, you solve by taking square roots. And that will give you a plus or minus answer. But in this case, it's just plus or minus 0. So like I can literally write x equals plus or minus 0. The square root of 0 is 0, but plus or minus 0 doesn't mean anything. So these have the same vertical asymptote. They both have a vertical asymptote at x equals 0. So I'm going to pull up Desmos so that you can see what this means visually. So you can make a connection between the equation and the asymptote and what it looks like. Because for me, I find just having a visual representation helps me understand better. So I'm going to start with the one here on the left. F of x equals -2 over x. So you can see how at x equals 0 here, our graph looks like it's becoming a straight line. That's what the vertical asymptote is. It's basically what vertical line it looks like it's becoming straight. And if I zoom out, you'll get to a point when you zoom out that it looks like it's exactly equal to x equals 0 right there. You know, it's basically a straight line. So that's what the vertical asymptote is. It's where does our graph start to become straight? And we're always looking for what x values does that happen. The other equation here has the same asymptote, but it's going to look different. It's going to have a different shape because it's a different equation, but the vertical asymptote is the same. So our second one here is 2x plus 5 over x squared. And it doesn't necessarily look like it's becoming straight at x equals 0. You can see like it might be at like -1 and then maybe at 1. But the key is when you zoom out, you can see that they're both sides here are heading basically to 0. And so our vertical asymptote is x equals 0, because as you zoom out, each side is getting closer and closer to that. And you might say, well, how do you know? Well, if I keep scrolling up, you can see that the two sides, the graph sides, the blue sides are getting closer and closer to our vertical axis here. They're just getting, you know, closer and closer and closer. They're never going to actually reach it because we can't have x equals 0. It's undefined if you plugged in 0 there, but it will get really close. So that's what the vertical asymptote is. It's like, you know, I can move my graph back to the center. It doesn't necessarily look like it's heading there at first, but as you get closer, you kind of zoom up to where it seems to be narrowing. That's our vertical asymptote at x equals 0. So are there any questions so far? Okay, so let's ramp up. So we've got 2x plus 1 over x minus 5. And then on the right, 2x squared plus 1 over x squared minus 4. So they're both rational functions. They've got x in denominator. What I've done is instead of just an x and x squared, I now have added a number to it. So you can see how that affects our vertical asymptotes. And you know the top has changed, but it doesn't really matter what the top is because vertical asymptotes is always based off of the denominator. So the 2x plus 1 over x minus 5, there's nothing to factor out. So we go straight to setting our denominator equal to 0. So I get x minus 5 equals 0. So you solve this. So all I need to do is add 5 to both sides. And we get x equals 5 as our vertical asymptote. our second equation, so there's nothing to factor out of 2x squared plus 1. It's not factorable because of the plus there. The denominator can factor, but I'm instead going to just set that equal to 0. We can solve it by factoring, or I can solve it by taking square roots. So I'm going to solve by taking square roots. So I have x squared minus 4 equals 0. We're going to add 4 to both sides. So we get x squared equals 4. Then you take the square root, and remember when you're solving and you take a square root, you get the plus or minus. So we get x equals plus or minus, and then the square root of 4 is 2. So we have two answers, 2 and negative 2. So we have two vertical asymptotes here, because there's two answers that make the denominator 0. So let's take a look at these on Desmos. So I will start with our f function here, 2x plus 1. Oh, I wasn't paying attention when I was typing. I thought I was deleted what I had. 2x plus 1 divided by x minus 5. Okay, so you can see that instead of having our vertical parts kind of at 0, it's now shifted over here, and it looks like it's kind of by x equals 5. You can see that this part is getting close to x equals 5 here. This part looks a little further away, but if I scroll down, you can see it's getting closer and closer. So our vertical asymptote here is x equals 5. Now, if you want to double check, if it's hard for you to tell, you can type in your vertical asymptote here, and it will give you that line. And as you scroll, you can see our red graph is getting close to the green line. And that tells you that it's a vertical asymptote there. And same thing when I go down in the other direction, the red line is getting closer and closer and closer to the green, and the green is our asymptote. So you can do that to kind of check yourself. I can even make it a dashed line, just because that's sort of how we graph them, as dashed lines. It's not actually part of the graph. The solid part is the graph. So the graph is what this looks like. We just kind of put the asymptote in there so you can visually see where it is. So that's matches. X equals 5 does look like the asymptote, and it should be, because that is correct. Now let's look at our g of x here. 2x squared plus 1. I actually put squared divided by x squared minus 4. Okay, so here, this has two asymptotes, and you can see that because there appear to be two places where our graph is becoming vertical. One here, which is at like -2, and then one here at +2. So you can see if I put in my vertical line for x equals 2, you can see that our graph is approaching that line on either end here. It's starting to go straight, and it's basically sort of becoming a straight line at x equals 2. The y values are basically going on forever. And same thing with -2 here. So you can see that our blue graph is approaching our asymptote, which is the green dashed line. So it's becoming more and more straight, or vertical at these points. So there are two vertical asymptotes because there's two locations where our graph appears to be becoming a straight line. But we have a gap between it because we can't actually equals that spot, because it will be divided by 0. So it's like your graph is kind of jumping and then it gets to another part of the graph. But at that location, it looks like it's becoming that, that vertical line, which that vertical line is special because it's like you somehow have all the values at once, which kind of makes sense if you think about the fact that you're dividing by 0, which is undefined. It's sort of infinity, but not exactly infinity. Like funky things happen when you attempt to divide by 0. And that's what we see here, is that when you're attempting to divide by 0, your graph is somehow at every point at once, essentially. You know, it's got these gaps, but it's pretty much trying to be everywhere at once along the y values. Are there any questions? Okay. All right, so now I've kind of flipped these. So on the left, again, I'm kind of doing like a linear on the left, x squared on the right. So on the left, I've got a linear, but I've got an x squared in the numerator. And on the right, the x squared both. So if you've got an x squared that looks like it can factor, like we've got a trinomial on the left, the x squared plus 2x minus 4, that is something that we can factor. So in order to find the vertical asymptotes, we need to factor before we find the vertical asymptotes because something may cancel out. We didn't do that before. Like I could have factored the x squared minus 4 on the right here, but I knew that wouldn't cancel out with the 2x plus 1. So that's why I didn't bother trying to factor. But we could potentially factor out an x minus 2. So we should factor here on the left to kind of verify. So this is where if you can get really quick at factoring, it's going to be a benefit. So I need x times x to get me to x squared. And then we're going to see, I need to multiply to a 4. And let's see, do I have that could be 2 times 2, but that's not going to give me a plus 2. 4 times 1, but that's going to give me a plus 3 or a minus 3 there. So you kind of go through because it looked like, okay, this might be something we can factor. And in this case, we can't. X squared plus 2x minus 4 doesn't actually factor. Because if I try, my only choices are going to do 2 times 2, which will actually end up having 0 in the middle because they have to be opposite signs. Or I'm going to get a positive 3 or a negative 3. So if you don't factor, then cool. But you want to try to factor first to see if it is factorable. Because if it is, then you start canceling things out. So here, nothing could factor, so there's nothing to cancel out. So we just go straight to making our denominator equal to 0. So you have x minus 2 equal to 0, which when you solve, you add 2 to both sides, we get x equals 2. So that's our vertical asymptote. Okay, now on the right here, we've got this 3x squared plus 8x minus 3 in the denominator. So if we factor, it's not going to cancel out with the 2x squared plus 1, but we have to factor anyway, because we're going to have to factor to set it equal to 0. So I'm going to just try to factor. So the 2x squared plus 1 doesn't factor, so I can leave that. But we're going to try to factor our denominator. So to multiply to 3x squared, I know I need a 3x and an x. And then I need, on the last parts, I need to multiply to a minus 3. So that's going to be just a 1 times 3. And then I have to get the right combination. I have an opposite, a positive and a negative. So if I put it in this order as 3x minus 1 and x plus 3, the outside will give me 9x. The inside will give me minus 1x. 9 minus 1 is 8x. So it works out. And then the negative 1 times 3 gets me a negative 3. So I was able to factor this. What I recommend that you do is, if you are not factoring by trial and error, is to factor separately and do your work on the side and then put it back in. Because if you're doing the AC method and you try to factor with the AC method in your denominator, it's going to be real messy. So for the factoring, I recommend doing that separately and then putting it back in once you figure out what it factors to. So nothing cancels out here. So we set our denominator equal to 0. So we have 3x minus 1 times x plus 3 equal to 0. So we're solving a quadratic here. We set each factor equal to 0. So we have 3x minus 1 equals 0 and x plus 3 equals 0. And then we're going to solve these for x. So the 3x minus 1, I add 1 to both sides, which gives me 3x equals 1. And then you divide by 3 and you get x equals 1/3. So that's one of your asymptotes. The second one, x plus 3 equals 0, you subtract 3 from both sides, you get x equals -3. And that's your second asymptote. So we have two vertical asymptotes. And in this case, so unlike our previous where they were the same number, just opposite signs, in this case, they are not. One's a 1/3, the other one's a -3. So let's take a look at these and graph them. It's a good way to check your answer. So for f of x, I've got x squared plus 2x minus 4. Whoops, I put a multiply divided by x minus 2. Okay, so this one has a fun shape. It's kind of got this weird angled thing going here. That's actually called a slant asymptote, but we're focused on the vertical asymptote, which looks like it's right about here, because this is where it looks like the graph is kind of going straight. So that looks like it's at 2. And so I can verify here. And yeah, so if I have x equals 2, you can see that our graph is approaching that line. It's basically becoming that vertical line at x equals 2. So that is our vertical asymptote here. So let's check our other one. Got 2x squared plus 1 divided by 3x squared plus 8x minus 3. So this one, interesting shape, but you can see this actually is a very clear vertical asymptote. I mean, it already looks like it's vertical right here. So this would be at the 1/3, x equals 1/3. So we can test that. So if I put in x equals 1/3, you can see that it basically does kind of line up with our graph. So that's one vertical asymptote. And then the other one is at -3. So when I put that one in, you can see that the top part of the graph and the bottom start to basically hit that line, or look like they're hitting that line. They don't actually hit it. So that verifies that our other vertical asymptote is at -3 here. Are there any questions?
All right, I have a stupid question.
There are no stupid questions.
I'm trying to figure out, because I'm following with the Desmos calculator on my cell. So I'm trying to figure out how you managed to get the line underneath the equation as you're building the equation.
That is so underneath your backspace, there is the button for the vertical bar, and then it's got a backslash that gets you dividing. No, wrong button. It's the other one, /. I don't even know what I'm hitting. It's the / where the question mark is. That's the one that will get you underneath.
Okay, then I have to do it on the laptop keyboard versus
yeah. You can, if you use the keypad on the cell phone, if you hit the division button, it will do the same thing. Because for a fraction, we're just dividing. Right. I have Desmos on my phone. I actually have not. I have it installed, but I don't normally use it on my phone.
Yeah, if I use the division right after the 4, if I hit the division sign, it puts it right under the 4, not under the whole equation.
That's why I have parentheses around it. So I had to put parentheses on the entire numerator so that it knows that the whole thing is part of the fraction.
That's what I didn't do.
Yeah, yeah. So if you're trying to, yeah, always put parentheses around the top and then do your division, because yeah, otherwise it's only going to divide the last part.
Gotcha.
Yeah.
Well, that worked.
Yeah, the parentheses are super important.
Just those little things. That's what tripping me up on all this stuff that we're doing, or on the quizzes and stuff. It's just the simple stuff.
Yeah, math, it is basically, math can teach you how to pay attention to details. If you want to do well in math, you have to pay attention to every little thing.
They left that ADD person out.
It is harder if you have ADD. I'll look at that. It is very hard. Because yeah, you get distracted.
Do I get graded on a curve now? No, I'm joking.
Unfortunately, there is no different grading based off of whether you've got ADD or not.
Darn it.
I know. There are other questions.
Okay, there we go. Nope, I think I got that working so far.
All right. Yeah, and you don't have to graph it every time to check. I just like to graph and check my answer. I just like the satisfaction of seeing what I'm looking at and making sure it's right. Okay, so these are my last two examples here. And these are both x squareds because those tend to get a little bit more complicated. And yes, you could have x cubed or x to the fourth underneath, but you're not going to be quizzed on any of that. If you had something like an x cubed underneath, then you have to find the zeros based off of what you've been doing with the polynomials, which means you have to do synthetic division, you have to do the rational zero theorem and all of that, and it's a lot of work. So generally when we give you rational functions to find asymptotes, you're not going to see above an x squared. But if you do, it's the same work. You just have to use all of that polynomial stuff that you learned to find zeros in order to find vertical asymptotes. It's just way more work. So we're going to try to factor here for the first one. I've got x squared minus 32. I know that I can factor 8 out of there. And the denominator looks like it can factor as well. So we're going to try to see if anything factors out because you need to simplify before you find your vertical asymptotes. So when I factor an 8 on top, I get x minus 4. So I just divide both parts by 8. And then the denominator here, I know I'm going to have an x times an x to get to the x squared. And then I need to multiply to 8. I need to add a 2, and I'm going to have a positive and a negative. So 4 times 2 gets me 8. And if I do a negative 4 and a positive 2, that gets me negative 8. And negative 4 plus 2 gives me negative 2. So here we have something that cancels out. The x minus 4 cancels out. So when we're looking for a vertical asymptote, we are not looking at what we started with. We're really looking at 8 over x plus 2. Because you're looking at the simplified portion. So you don't care about the x minus 4. That's going to be something special called a whole. And I'll kind of show you that when I show you the graph. But it's not a vertical asymptote. So once you simplify, we set the denominator equal to 0, so that's x plus 2 equals 0, which gives us x equals negative 2. So I'm going to just graph this one before we go solve the other one. So 8x minus 32 divided by x squared minus 2x minus 8. Okay, so x equals negative 2 is our asymptote. And so if I kind of scroll up, you can see that our red graph, the actual graph part, is getting close to that line at x equals negative 2. And going in the other direction as well. The value we canceled out, x minus 4, if you set that equal to 0, you get 4. So notice for x equals 4, we don't have an asymptote. It doesn't look like it's becoming a vertical line. And that's because it's not a vertical asymptote, even though it's in the denominator. It's actually a hole. So if I get close, you can see, so when I'm scrolling here on Desmos, it's probably really hard to see, but it becomes an open circle here because at 4, it's actually undefined. So that's why it's called a hole, because we don't actually have that value in the graph, but we have every value close to it. And so it's like you just got this little gap in the graph at that point. But it's not a vertical asymptote because it's not looking like it's becoming vertical. So it's still based off of the denominator, the denominator equaling 0. But because it's not looking like it's vertical, it's not an asymptote. It's something else. It's just like a little hole here. And you can't see it graphically because of the way that Desmos and all online graphing, even a regular graphing calculator, they usually don't mark it as a hole. They'll connect it. And even when I zoom in, they will connect it. You only see it if you know to look for it. Just the way that these calculators have been graphed or coded to do is they don't put the open circle there. Well, they really should. They really should, but they don't. So you have to kind of know to look for it there. But that is the difference when it cancels out, because when it cancels out, it's different from a vertical asymptote. So they're both in the denominator, but they just look very different things. So let's look at g of x here. So we've got 2 over x squared plus 49. So there's nothing to factor out. So I can just set the denominator equal to 0. And so we have x squared plus 49 equals 0. And so we're going to solve for x squared. We can solve by taking square roots. So I'm going to subtract 49 from both sides. And we get x squared equals negative 49. So I'm going to take the square root of both sides, and we're taking the square root of a negative. So we're going to get imaginary numbers here. So I have x equals, I'm going to have a plus or minus because we're solving, we're taking a square root. The negative is going to give me an I, and then the square root of 49 is 7. So I'm going to get plus or minus 7i. Imaginary numbers cannot be graphed on the graphing system that we are using. You will, if you are a math major, you eventually learn how to graph imaginary numbers, but you guys are not math majors. So as far as you're concerned, imaginary numbers cannot be graphed. So what that means is that there are no vertical asymptotes. So not every rational function has vertical asymptotes. Most of them do, but not every one. So this is one where there is no vertical asymptote, because when you try to find it, you get an imaginary value, which you can't really graph. So let's put this one on Desmos. Just 2 over x squared plus 49. I might need to zoom in. Sometimes it's like, do I need to zoom out or do I need to zoom in to see the graph? This is not an interesting graph. So it just looks vertical here. It's gotta be. Sometimes we get funny graphs like this. I never know, is like zooming out or in makes it more interesting. And apparently in this case, either way, like you can see that if I try to click our y values are getting kind of really close. It's just like 0.004. It starts at 0.0 for one of 0.04. It's actually getting a little bit smaller. It's kind of approaching 0. So I think I'm going to have to mess with my graph because we're going to need a really huge x-axis for you to really see the shape here. Okay, here we go. So this is what this one looks like. And if you didn't know that this is what it was going to look like, you probably would have thought it was just a straight line. And that gets you to something else called a horizontal asymptote that we will talk about, because this has a horizontal asymptote, but it doesn't actually have a vertical asymptote because there's no spot where it doesn't, makes a straight line. Like it looks like here, it's becoming a straight line, but we don't have any values that are excluded. It comes back down again, it stops. What's special about the vertical asymptote is that it looks like it goes on forever. It goes to infinity. This isn't doing that. It's not at this point here at x equals 0. It's not going to infinity, going all the way up, or it's not, it's stopped. And that's why it's not a vertical asymptote, even though it looks like it's becoming vertical. The special part about that vertical asymptote is that it looks like it's going to align forever. And so this is not. It's going up and then it's coming back down. So there is no vertical asymptote for this particular rational function. So it does have other types of asymptotes. It has a horizontal asymptote, but it's important to know that not every rational function has a vertical asymptote. It's possible not to have one exist at all. And so that will always happen when you're getting an imaginary number, when you're trying to set the denominator equal to 0. So that's sort of your key. If you're solving for your vertical asymptote and you end up with a complex number, then there's no vertical asymptote. Or if there's like a, if you don't even have a variable in the denominator, there's no vertical asymptote. Any questions? Okay, so that's vertical asymptotes. And that's how you find them. This is why you had to learn all of these, how to solve all these equations, because then we start using them once we start looking at graphs. And if you're wondering, why do we even care about vertical asymptotes? These actually do pop up in engineering and electrical engineering. So for those that are going into electrical engineering, it's important to be aware about these. For those that are going into maybe computer science, you need to know about them, so that if you happen to be programming something that is a rational function, you need to be aware that there's going to be problems where you might accidentally, kill your program if it's trying to divide by 0. So that's where I can see somebody going into computer science maybe needing to know about this. Other fields, I don't necessarily think you need to really know about vertical asymptotes, but they're cool. I think rational functions look really neat. So I like them because they're not boring like a line. They have these interesting shapes.